This episode of Real Engineering is brought to you by the Curiosity Stream deal. Now just $11.59 for an entire year until
I don't think it is fair to speculate on what God might or might not be able to do. Rather, we should examine what he actually does within. All are attest that it operates according to well-defined laws. These laws may have been ordained by God. He does not intervene in the universe to break the laws. At least he has set the universe going.
In the cold universe, no light could escape the dense, opaque fog. As this cosmic soup of atomic particles down, hydrogen atoms began to form, leading to these bright, violent new stars, burning through the fog to all light from escaping the expanding universe. These early photons have travelled unhindered through the vast of space for 13.5 billion years. Their final destination here on the man-made detectors telescope. A space odyssey coming to an end because of humans. The James Webb Telescope is going to give us a detailed glimpse of this early universe from which we know was born. The James Webb Telescope is a $10 billion an endeavour that has eaten into NASA's limited budget, 1/4 of NASA's entire astronomy budget and in the early hours of a tenuous launch date of December 20th, $10 billion gamble will launch aboard the Ariane 5 European heavy lift launch vehicle from the European spaceport, French Guiana. Astronomers, physicists and enthusiasts look on with nervous excitement as this rocket carries the next generation curiosity. This is the insane engineering of Space Telescope. The combination of technologies make the James Webb Telescope possible are unique to this time in human history. The launch vehicle, the image processing, the electrons, the cooling systems, the mirror, and the Sunshield is the culmination of not just decades of work from the engineers NASA, but thousands of years of work of our ancestors. Materials and engineering required to peer back 13.5 years into the reionization epoch are in human history that we, the human race, should be watching with bated breath together. The launch will take place in Guyana, a spaceport ideally located on the Earth's equator. James Webb Telescope, an extra push towards its final destination. Webb Telescope will not be in orbit around Earth like Hubble. Will be launching to a destination 1.5 million kilometers, Lagrange Point L2. Lagrange points are special points in small objects like satellites can stay more or less in the same to the gravitational bodies that they are traveling with. This the gravitational pull from the two bodies precisely equal force required for the object to move with the gravitation, like little parking spots in space that allow satellites to sit in a position while using a minimal amount of fuel to stay there. There are 5 Lagrange points between the Sun and Earth. L1 like Earth. It's extremely useful for sun observation satellites. The nature of the James Webb Telescope's job wants it to avoid them as much as possible because it is an infrared is heat, and the heat emanating from the sun saturate its sensors and make observing the cold impossible. So it will be launching to L2 about here. Here the telescope can turn its back to the sun and moon, which will stay in the same position, nicely lined up the telescope. Thanks to Lagrange Point 2's unique physics. In order to operate correctly, the dark side of the telescope needs to minus 233 degrees Celsius. Without the heat from the sun and Earth, the telescope would be scorched at 8 Celsius, nearly hot enough to boil water. This is a heat to block, and to do this, the James Webb Telescope will carry yield on its back like a tortoise.
And making such ice is a very, very tough problem.
That's Mission Systems Engineer for the James Webb Telescope.
Every heat flow to make sure that we do not let any heat through from the hot side to the cold side. To make sunlight, which is dumping approximately 200,000 watts onto the in our direction, we want about a watt of that to make it through to the telescope. It really cools down to those temperatures.
Preventing is, as Mike said, a very tough job. Heat 3 ways. Conduction, where heat is transferred from atom in direct contact with each other, like heat traveling down a cup. Convection, where heat is transferred from the physical movement of radiation, where heat is transferred by electromagnetic wave. In the vacuum of space, convection isn't a concern, leaves conduction and radiation as methods of heat transfer. How the James Webb Telescope is managing these. First, the Sunshield needs to be light, strong, resistant from solar radiation, dimensionally stable across a range of temp and reflective. That's a long shopping list of requirements. The type of high-performance plastic manages to check all the boxes. Layer of the Captain's Sunshield is incredibly thin. Layer closest to the sun is the thickest at 0.05, while the next 4 layers are just 0.025 millimeter. Captain by itself is actually transparent, which isn't trait for a sun-blocking heat shield. Thankfully, the one is Captain can be easily coated in other materials, coated in a 100 nanometer thick coating of aluminium, its reflective appearance. This reflective quality helps transfer through radiation by simply bouncing that radiation, and with the gaps between each layer, the heat that is easily transferred through conduction or convection, taking a highly insulating vacuum of space between each layer, transfer between each layer through radiation. The outer gain heat and start glowing with infrared radiation, just through an infrared camera. In order to prevent this, the clever engineering designs. The layers are angled relative to ensure the reflected radiation between each layer outwards to space, ensuring that each layer gradually picture as it gets closer to the critical components in the instrument. The layers gradually get smaller in area from layer 1, ensuring the mirror only has a direct line of sight with it at all times. Layer 1 itself is also silicon coating 50 nanometers thick, giving it silicon was used because it has high emissivity. It emits a lot of energy it absorbs out as thermal, meaning the material will not hold onto its heat, which would get through the structure of the spacecraft to areas we want to cool. High emissivity silicon coating is applied to layer 1 and 2 hottest layers, helping them send their heat back out to space from the spacecraft as fast as possible. These design choices the heat shield to maintain the massive heat differential between sides. But blocking heat is just one challenge.
It's one of the bigger challenges, along with just designing a system that does this complicated, and necessary reliably and correctly.
In order to fairing of the Ariane 5 rocket, the Sunshield has to be folded before launch, leading to some incredibly complicated to ensure it unfolds correctly when game time arrives.
Deploying things in space is always difficult, but when you're deploying rigid structure, that's generally what us engineers would call deterministic. That's easy. Membranes and cables are almost inherently non-deterministic. You want to, describe or illustrate what that means, try pushing, the string will move, but if I ask you to determine what it will assume, you will have a very, very hard time doing that. To control these almost non-deterministic things takes a great deal of effort, a great deal of trial and error. And even after we're getting the design right, the one thing about the Sunshield, it's almost like a parachute, or it's very similar to a parachute. But it's also only as good as the very, very last. And you're going to find out whether you folded it correctly or when you use it.
The unfolding process will begin not too far from Earth, starting with relatively simple solar panels and communications antenna deploying. The process begins on day 7. As the spacecraft is coasting to, there are over 300 single points of failure in this, 300 chances for a $10 billion 25 end, 107 pins holding the Sunshield together released on cue to allow the system of pulleys, motors, and springs to begin unfurling the Sunshield into its complete shape. This process will take 3 days, and once optical components will unfold and lock into place. Complete process, but we are most certainly not in the clear. The hood of the tennis court-sized Sunshield being struck by micrometeorly high, and because this is a thin layer of plastic stretching, a small tear caused by an impact could cause a run through the whole Sunshield. To prevent this, ripstop slid into the Sunshield, which will arrest tears and keep them a single portion of the shield without compromising structural. The film has also been carefully molded with corrugations and other and shaped the shield as needed. This passive cooling system, ensuring the dark side of the telescope is shielded from keeping its sensitive heat detecting instruments at 40 degrees, about minus 233 degrees Celsius. But telescope, specifically the mid-infrared detection instrument, needs to be even colder to work correctly. 7 degrees Kelvin. just 7 degrees, absolute minimum temperature of the universe of 0 degrees Kelvin. We need active cooling. The James Webb Telescope includes a cryocooler for this purpose. The challenge in developing alone was immense, costing $150 million. Getting cold temperatures is just one small part of the design. It has to be eliminated, as the tiniest movement of the telescope massive blurs in the image as it attempts to focus on billions of light years away. That means eliminating moving parts, and when that can't be done, incredibly precise machining is needed to balance weights as they move. The cooler uses a tiny amount of electricity, as the telescope only has 2,000 provided by its solar array, and it needs to run years. That means a closed-loop cycle, with our being continually reused. I found this explanation on NASA's site. The pre-cooler features a 2-cylinder hose pump and cools helium gas using pulse tubes, with a regenerator acoustically. Okay, horse with carefully balanced pistons that will cut vibration as the weights, but the rest of that explanation sounds like it came straight out of novel. A sound wave is just a pressure wave, with pressure and technically proportional. Higher pressure will cause higher temperature. One advantage of this is by creating a standing wave, where the peaks are stationary. We can do this in a closed tube, where the root of the tube is determined by the tube's length. Here, the sound will closed end and create a region of compression and high pressure, high temperature. This alone isn't terribly useful. The energy in the system will stay relatively stable, left on its own. What if we could extract some of this heat with each cycle? Then we could gradually cool the overall system. To do this, as energy out of the system. This is done with a stack, air gaps that allow sound to pass through it, which is placed so that it's both the hot region at the end of the tube and the cold region in the center. A heat exchanger is then placed on either end of the stack, and one for the cold. The hot heat exchange will conduct its heat, Sunshield, where it can radiate out to space, while the cold portion, heat, or lack thereof, to a copper plate attached to the back sensors to cool them to 6.2 degrees Kelvin. Obviously, an extreme oversimplification of the act of the pulse tube cryocooler. This is just a basic of the physical phenomenon that allows it to work. The cooler is quite possibly the most fascinating part of this spacecraft, utilizing a simple physical phenomenon with extreme precision. Those infrared sensors located in the center of the telescope's beam to work. The golden mirrors are the most striking part made of 18 hexagonal segments, 6.5 meters. So, what's the deal with the design? It's unlike I have ever seen. The mirror surface itself is beryllium. That's a unique and expensive material choice. We need the structure of these mirrors to remain in an extreme to reflect light as desired. They can't bend with temperature changes, and they also need to be extremely light launch costs. Beryllium is a lightweight metal. With an just 4, it's much lighter than silica glass, a more traditional surface material, while being far more capable in dealing temperatures the mirror will operate in, keeping its shape and not contract that it ruins the carefully shaped curves of the mirror. While no strong as steel, beryllium is much stiffer with a Young's 100 gigapascals. This means that while beryllium is than steel, it's harder to deform before it actually breaks, giving it excellent dimensional stability. On a pound-for-pound, beryllium is 6 times stiffer than steel, making it the material for this mirror. However, it is not for that we need to turn to gold. Gold is not of visible light, being particularly poor at reflecting the light of the visible spectrum, giving it its distinctive golden hue. Critically, it is an excellent reflector of the infrareds while being very unreactive, ensuring the mirror surface will not lose its shine during its operation. To reflect that light, coat, just 0.1 micron in thickness, is coated with beryllium subsurface, taking just 48.2 grams, about the same weight as a golf ball. A surprisingly small amount, which has a collecting area about 25 meters squared, 5 times larger than Hubble's 4.5 meters squared. The mirror needs to be massive, and to explain why,
Well, I could tell you how much it's collecting. First, where stars or stellar objects or things be a nanojansky. And to explain what a nanojansky is units of brightness. It's very, very dim. We're looking for among the sky. If I was to put a child's nightlight, put it on the surface of the moon and look at it from the Earth, the source would appear to be 20 nanojanskys. So we're looking for our 1/20th as bright as that. To do that, you need a big telescope. Picture light as rain. You want to collect a lot of rain, you make a big, wide bucket. At the size of our bucket, 6 meters across, we're only 1 photon per second, 1 particle of light per second. I'll go out tonight or any night and look at the brightest star there is in the sky. Is probably collecting about 1 million photons from that star. So to see these very dimmest things there are to see in the universe, you need a light bucket that's 6 meters in diameter.
1 foot really puts things into perspective. Mike and the rest of the James Webb Telescope actually wanted the mirror to be bigger. Launching a mirror that size, between the increase in weight and limited inside the Ariane 5 fairing, was not cost effective. They maximized the size with the resources available, and even though the mirror's collecting surface is 5.5 times, the James Webb mirror is 62% lighter than a solid glass mirror. That is an astounding weight driven by launch weight requirements to get the telescope to L2. The mirror is even programmable. When Hubble transmitting images back to Earth, it became clear that there was the telescope's optics. Instead of the crisp, awe-inspiring all familiar with today, the early images came back blurred. The mirror had been ground down to flat by a mere 1/50th the thickness of a human hair, but caused the light to be focused incorrectly on the telescope sensor. Replacing the mirror was not an option, but Hubble was designed throughout its lifetime, featuring modular equipment bays that allowed to be removed and replaced. In order to correct the issue, were installed into one of these equipment bays, like a classes for the $1.5 billion telescope, will not be serviceable. It's simply too far away from Earth. Any space vehicles capable of carrying humans to service. If there was a problem with the mirrors, that would be game over. But we're not taking chances this time, and have engineered a system adjusting its focus by itself. Each of the 18 can contort its shape and adjust its position relative to located in the main mirror's focal point. The grid rear side of the beryllium mirrors are assembled with the struts and motors that can not only adjust the mirrors, but with the center motor and these struts, the mirrors can act curvature to adjust the focal point of the mirrors. It could have corrected Hubble's issues from Earth. Once fully deployed, will begin its calibration phase, with each mirror adjustable. Each of the 18 segments have aligned correctly with the secondary, a 0.74 meter convex mirror, which itself is to adjust its position. These motors and control systems are precise that the mirrors can adjust their positions in steps of wavelengths of light, creeping closer to alignment to 1/10,000th the size of a human hair. Is an astoundingly accurate electromechanical system of the James Webb Telescope. Performed this calibration test here on Earth. Absolutely massive vacuum chamber that can be cooled down temperature that the telescope will operate at, ensuring can be achieved. But the job to get a clear image with primary and secondary mirror alignment alone, they focused to the Cassegrain focus, which is located inside the aft optic. This black protrusion in the middle of the primary mirror, light from entering the aperture. In the darkness within, there are two, one of them being the fine steering mirror, and this thing's most expensive image stabilization tool. It is a fine guiding system. The fine guiding system is locked onto it, and its job is to keep that star in the center of its field of view. 64 milliseconds, the fine guiding system will send signals to the control system to make adjustments to ensure the telescope's hit. This attitude control is done with a combination of cells located inside the spacecraft bus below the heat sheet with the fine steering mirror. This mirror will constantly to ensure the target of the telescope stays steady on the sensitizing blur. The telescope also has thrusters for larger 191 liters of hydrazine and 95 liters of its oxidizer, dinitrogen tetroxide, will be beside the spacecraft bus that will feed 20 different rocket thrusters around the telescope. There are 8 thruster modules, 2 of the spacecraft bus, to aid the reaction wheels in spinning the telescope towards points of interest. These 16 engines will be fed only a monopropellant reaction where the hydrazine is passed over, causing a highly exothermic reaction, breaking the hydrogen, and ammonia. The other 4 motors in positional control and require more power. They will be hydrazine and dinitrogen tetroxide. This fuel will react hypergolically to form nitrogen and water, meaning they do not need an igniter, They simply ignite on contact. Hydrazine is an excellent choice for a long-lasting mission like this. Ergolic reaction means the motors can repeatedly and reliably fight failure, causing issues like an igniter breaking. Hydrazine is for long periods at room temperature, allowing it to be stored over the life cycle of the James Webb Telescope. Unfortunately, cycle is limited to 10 years precisely because of the fuel. In orbital maintenance, we will run out of fuel at some point. It has no way of refueling the telescope. But rumors seems NASA is looking to develop the technologies required to fuel the James Webb Telescope before its demise 10 years from now. It's capable of refueling spacecraft far from Earth, isn't it? The James Webb Telescope could end up teaching us many more beyond the early stages of the universe.
It's my hope of being 25 years on this job that eventually scopes, the really, really, really big ones of the future, will be testing James Webb that's designed to work in space has been a very do on the ground. And I'm hoping that some things in space, testing them in space, tweaks, and then deploying them in space that way.
We are of a new space age, and the James Webb Telescope is on our journey towards being a more capable spacefaring. This is just one of many milestones in our brief time as a speedball of escaping our planet's gravity. From building our incredible glowwork and sending satellites to the far reaches of our solar system, moon, and building reusable rockets. It's never been more aerospace enthusiast, especially when you can get access to the Curiosity Villa bundle deal for just $11.59 a year. This holiday access to incredible space documentaries on Curiosity Stream for a month. And with that yearly subscription, you will get full access to a series launching in the new year and our 9-part logist that is ready for you to watch right now. This discount will end December, so you have less than a week to avail of this deal. Filler gift for the documentary fan in your life while supporting this effective way possible. Nebula gives us a place to experiment inside worry of alienating our current audience on YouTube or being demonetized of topics like war. Your support there has helped this channel evolve, and we are able to give you exclusive content like this as our thanks. Many of you will be happy to hear that we finally released a Roku app for Nebula. More options on how to enjoy our ad-free videos. The best way to channel is by signing up to Nebula through the Nebula and Curiosity for just $11.59 a year. With access to both Nebula's award-winning documentaries on Curiosity Stream, like this amazing trajectory that tracks the scientific milestones of space science, you can sign up to this amazing deal by clicking on this button on screen. If you're looking for something else to watch right now, you could watch our last video on the sonic travel, or you could watch Real Science's latest video on the of Orcus.